Hello everyone, I am Kausal Patel from Mechanical Engineering Department at Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. In this video, we are going to discuss about undamped free vibration and then we are going to derive the equation of simple harmonic motion. Undamped free vibration. Now we have already studied what is free vibration. So whenever an external force is removed after giving an initial displacement to the system from its mean position, then the system vibrates on its own due to internal energy or elastic energy it possesses. Such vibrations are known as free vibration. Now, during free vibration, if there is no damping resistance provided externally to the system, then the vibrations are known as undamped free vibration. Okay, so we already know that artificial damping resistance is provided externally to reduce the amplitude of vibration. Now if no such damping resistance is provided to the system which is having free vibration, then the vibration is known as undamped free vibration. Okay, theoretically for undamped free vibration, the amplitude of vibration remains constant. It is not going to reduce with time as there is no energy loss during each cycle of vibration. But in real practice, the system is always subjected to small damping, like damping due to the viscosity of air, then damping due to the friction at microscopic level, that is nothing but solid or structural damping. So it is nothing but a friction between molecules of the system, and due to that friction there is some heat loss during each vibration. So if such small damping is there, then the amplitude of vibration gradually reduces and finally the system comes to rest at its mean position. However, if such damping is very small, then we can neglect that damping and the vibration of such system is considered as undamped free vibration. Now we already know that the frequency of undamped free vibration, that is known as natural frequency of the system, which remains constant for the given particular system. The natural frequency of system is by far the most important parameter in vibration analysis. So it is necessary to determine natural frequency of the system. So if the system is subjected to dynamic excitation forces, then it is essential to estimate the natural frequency to avoid resonance condition. Okay, it means the designer should design the system in such a way that its natural frequency would not lie within the range of working frequency, and that's how he can avoid the resonance. So it is essential to determine the natural frequency of the system. Now to determine natural frequency of the system, we need to first of all determine equation of motion for the system. Okay, now as the vibration is in the form of simple harmonic motion, then we need to also determine the equation of simple harmonic motion. Then by comparing the equation of motion for the given system and the equation of simple harmonic motion, we can get the natural frequency of the system. So now we are going to determine the equation of simple harmonic motion. Okay, to determine equation of simple harmonic motion, we are going to use second definition of simple harmonic motion, which is we have discussed earlier. So as per that definition, simple harmonic motion is the motion of a projection of a particle moving around a circle with uniform angular velocity on a diameter. So to understand this definition, we are going to consider a small particle which is moving around a circle with angular velocity like this. Okay, so the simple harmonic motion, that is nothing but the motion of projection of a particle, not a particle, on its diameter. So here we can get the projection of particle at any instant of time let at time t is equal to 0 the particle is in this position. Now after t second it moves to this position, so it has advanced through this much angle, and this angle could be represented as omega into t, as the angular velocity of this particle remains constant and it is omega. Now during time t second it advances from this position to this position. Now we can study the motion of a projection of the particle on horizontal diameter or on vertical diameter. Okay, so the motion of projection of particle would be the simple harmonic motion. It means here the particle is having circular motion with constant angular velocity omega, but the motion of projection of particle, let the projection of particle on vertical diameter, then it would be like this. Okay, so it is nothing but a to and fro motion about the mean position. This would be the mean position for the motion of projection of a particle, and it is simple harmonic motion. It is not necessary we can always take the projection on vertical diameter. We can also take the projection of particle on horizontal diameter. Then the motion of projection of particle would be like this, and in this case this would be the mean position. Okay, in both cases we can get different equations, but in this particular case we are going to study the motion of projection of particle on this vertical diameter. Now in t second this particle moves from this position to this position. Okay, so at this position this capital X represent the position vector. Here capital X, that is nothing but the radius of this circle, and it is also the maximum displacement of the projection of particle from the mean position, and that is amplitude. Okay, so this vector X that represent position vector. Okay, now we have to find out the equation of displacement of a projection of particle from the mean position at any instant of time. So as this particle moves around a circle with constant angular velocity, its projection on vertical diameter is also going to change from the mean position with respect to time. So we need to find out the function, that is displacement from the mean position, and let it be denoted by small x. Now this displacement from the mean position at any instant of time could be represented from this geometry. Okay, so from the geometry we can see that here this position vector is having angle omega t with the horizontal. So here at this position we need to determine the displacement of projection of particle from the mean position. The projection of particle would be at this position at this particular instant of time. So we need to find out the displacement from the mean position, and it would be this much displacement. So this much displacement can be found out by taking vertical component of this position vector x, and the vertical component of position vector x, that would be capital X sine omega t, because here this angle is omega t. So ultimately here the displacement of a projection of particle from the mean position on vertical diameter, it could be represented at any instant of time as x is equal to capital X sine omega t. Okay, now if we would have taken the projection of particle on horizontal diameter, then this would be the deflection from the mean position. Okay, so in that case equation would be x is equal to x cos omega t. But here in the present case, displacement at any instant of time of a projection of particle from the mean position, it could be given as small x is equal to capital X sine omega t, where capital X that is the maximum displacement from the mean position, and it is nothing but the amplitude. Okay, so here we can see that the displacement at any instant of time from the mean position, it could be given by x sine omega t. Now from the equation of displacement we can get the velocity and acceleration by taking first order differential and second order differential with respect to time correspondingly. So by taking first order differential of this equation with respect to time we can get velocity, and by taking second order differential of this equation with respect to time, then we can get acceleration at any instant of time. So here we have determined by taking first order differential with respect to time, velocity can be represented as x dot is equal to omega x cos omega t. So it is the differentiation of x is equal to capital X sine omega t, where capital X, that is amplitude, and it remains constant. So the differentiation of sine omega t, that is according to the chain rule, the differentiation of sine omega t, that would be cos omega t, and then the differentiation of omega into t, that would be equal to omega. So finally the velocity x dot can be written as omega into x cos omega t. Okay, so from this equation we can get the velocity. Okay, same way by taking second order differential with respect to time we can get an acceleration. Okay, and acceleration, that is second order derivative of displacement with respect to time, that is also represented as x double dot. So here x double dot is equal to minus omega square x sine omega t, that is nothing but the first order differential of this equation. In the differentiation of omega x cos omega t, here omega and x are constant, and the differentiation of cos omega t according to the chain rule, it is minus sine omega t, and the differentiation of omega t, that is omega. So ultimately total differentiation, that would be minus omega square x sine omega t. Okay, here the equation of velocity could also be represented like this: omega x sine omega t plus pi by 2. Okay, so it is taken in the form of sine, then it could be represented like this. Now by comparing this equation with the equation of displacement, we can see that here in sine term there is a phase angle. So from this equation we can see that the velocity vector is going to lead the displacement vector by pi by 2. In the same way, the equation for an acceleration, it could be also written as omega square x sine omega t plus pi. Okay, so here we can see that the acceleration vector, it is going to lead the displacement vector by pi. Okay, here the vector of acceleration, it is also going to lead the velocity vector by pi by 2. So these things we already know in vector diagrams, in velocity analysis and acceleration analysis in kinematics of machinery. Okay, now from the equation of an acceleration, okay, we can see that it would be maximum when this sine term would get maximum. It means whenever sine omega t would be equal to 1, then the maximum acceleration of system, it could be minus omega square x. Here negative sign, that represents the acceleration is always directed toward the mean position. Okay, so for maximum acceleration, x double dot could be written as minus omega square x. Okay, so now from this relationship we can write down x double dot plus omega square x is equal to 0. Now this is the equation of simple harmonic motion for longitudinal vibration. Okay, so this equation is very most important because we are going to find out the equation of motion for the given particular system, and then we are going to compare that equation with the equation of simple harmonic motion, as all vibrations are in the form of simple harmonic motion. So that's how, by comparing the equation, we can get the value of omega square and the value of omega, that is the natural frequency of the system. Okay, in this case here omega, that is nothing but circular frequency of a particle, and it is assumed to be constant. Okay, so this equation is for longitudinal vibration. Now if there is a torsional vibration or oscillations, as in case of simple pendulum, okay, so here the linear acceleration is replaced by angular acceleration, that is theta double dot, and linear displacement x, that is replaced by angular displacement theta. So the equation would be theta double dot plus omega square theta is equal to 0. So these are the equation of simple harmonic motion.